So, today what we're going to do is we're going to talk about something called probability trees. This is simply another way of organizing your information like the two-way tables were, right? And by having organized information, we can do those compound probabilities very easily. So a two-way table is good for just looking at one piece of information versus a total. But a probability tree will allow you to look at multiple different experiments, right? So we're looking for a red car and a blue car, right? So if it's an and situation, what can I already conclude from probability trees? What am I going to be using? Multiplication, you betcha. Okay? All right, so don't forget what we have done as we move through the new stuff. So many of you have already seen probability trees before. We're going to go through a few basic facts of them because remember what happens is, even though this is things you've seen before, each level as you move forward, level 2, level 3, etc., you see the same type of material, but they just build on it what we've done before, so you need to be careful. I am going to warn you that probability trees were killing the students last year. Yay! But if you know that probability trees are sometimes difficult, then that means you need to pay close attention to them because they seem very straightforward. Now, the good news is I know which parts of a probability tree now, after having done this last year, that they were having trouble with. So I can focus your work a little bit, okay? Now, that doesn't mean y'all might not have any problem with it at all, but so I can show you where the issues came up and what brought them up. All right, so let's just go to our Education Perfect and look at the information from there. It says a tree diagram can display all the possible outcomes for a particular situation. Some probability problems are easier to solve using tree diagrams. So what we're going to do today is we're going to look at the basic structure. All right? So what you need to write in your notes is a tree diagram, also known as a probability tree, is simply a way to display all of the possible outcomes and probabilities for a particular situation. Okay? So there's what you need in your notes. A tree diagram, or probability tree, is just a way to display all the possible outcomes and probabilities for a particular situation. Okay? So you can have lots of different experiments, lots of different outcomes happening there, and we're going to put them all together using a tree diagram. So the first thing is we're going to review how to draw just a basic tree diagram, and then we're going to talk about reading them. And then we're going to learn how to take a tree diagram that was like that probability chart. It gave you a little information and you had to fill in the rest. Okay? So, here we go. So, here's an example of a tree diagram that lists every possible outcome. All right? And what we're doing here is this one is measuring what happens when you toss a coin and throw a die. Now, at the same time doesn't mean that means your coin and your die are going to get stuck together, right? That just means you're going to get two different things happening. You're going to get a coin and you're going to get a die. It doesn't matter if it says at the same time. It could be one after another. You're still going to have the same result. A couple of things about building a probability tree that I like to do that they don't do all of them. They do some of them, but they don't do all of them. And this is what got the students into some trouble last year. Okay? The first thing is, I think you should always write the word start at the beginning of every tree diagram. So here, I would have the word start. Now, and let me explain why I believe that. And this is, again, one of the things that caused them trouble. Okay? Usually, you start with nothing. I haven't tossed the coin yet. I haven't rolled the die yet. I haven't done anything yet, right? And in that case, you just write the word start. However, what if it says that you're going to draw 3 balls out of a bag and you've already drawn a red one? Yeah, you're not starting with nothing. Here you would have red as your starting point. Do you see that? And now it's pretty rare. It almost never comes up in your homework. But guess where it does come up? On the assessment. Okay? So be careful. Yes?
How can I write that over like what you just did as a note so that I can remember that?
Well, okay, so usually you start with nothing, but could start with some event. How's that? Does that make sense? Because event is what happened, right? What you get. So you get a heads, that's an event. Okay? So you could start with an event. Like last time they had one where they had like bottles of milk, and the woman had already bought 2 bottles of milk, and no one was getting the 2 bottles of milk in the beginning. They were thinking start with nothing. So be careful. If it tells you you've already done something, then that needs to be there instead of the word start. But in my mind anyway, writing the word start kind of makes you focus on, do I already have something here? Okay? Then you'll get, the same number. Remember that hashtag is the symbol for number. It doesn't always just mean you're on Instagram or whatever, okay? So, all right, same number of branches as outcomes. For the first event, or for the first experiment. Now write that down, and then I'll explain it. And you might need to add or subtract or rewrite what I say. The way it makes sense to me might not be exactly the way it makes sense to you, right? So you can always reword these, as long as you're not changing the meaning of them. So for example, in this case, what experiment am I doing first? A coin. Now, in reality, they say I'm doing these at the same time, and so I'm really just doing them at the same time. But the reason they chose the coin first is because it has fewer outcomes. It makes your tree smaller. So that's not a rule, but in general, if one experiment has a smaller number of outcomes, then write its possibilities first, right? Because when you flip a coin, you can only get a what? Heads or a tails. That's only 2 branches. Okay? But if you roll a die, you can get a what? 1 through 6, right? That's 6 branches. So do you see, though, the total number of outcomes tell you how many branches? So, okay. Now, something else that I like to do that they're not doing is label each experiment. And I like to be explicit, okay? So here I would say flip coin as the heading for that. And again, because it tells you what you're doing. Now, Alternately, you could say, or first experiment. If you don't have, if you're running a race, for example, and you're doing the best 2 out of 3, then the heading would be first race. Then the next heading would be second race, right? Okay? Or first event, second event, something that tells you what it is that you did there. Okay? I'm going to have to erase a little bit of that because the or is taking up some space that I'm going to need for this second one. So the first one, I flipped a coin, right? Tells me what I did. And again, do you think you're not going to get the probability right if you don't flip a coin on there? Probably not. Do you think you might be more aware and careful about what you're writing if you label things? All right? So this is not about you won't get it right if you don't label it. This is about making sure that you stay focused and organized, which is the thing with statistics. Probability, Okay? All right. Everybody okay with that? Label each experiment. Okay? Step 4. Okay? Then you're simply going to draw the new branches from the original branches. So if you have another experiment, you don't get a new tree diagram. You're just going to be branching off of the one you started with. Okay? So from each result. So, for example, here, I could get a heads or I could get a tails. And from each one of those results, I'm going to get a new set of branching. Okay? What was the second experiment we did? Toss a die. Yeah. And I was teaching this morning, and I just wrote die on there, and they said that looked too harsh. So toss a die. How's that? Okay. So toss a die. And if you toss a die, you get a 1 or a 2 or a 3 or 4 or 5 or a 6. That's where these numbers are coming from. Those are the possible outcomes when you roll a die, right? Make sense? And we get the same number of outcomes from when we get heads, and then we do exactly the same list down here when we do the tails. Looks good? Okay. What if I then, drew a card? Each one of these would then get a bunch of branches. Hopefully not draw a card, because how many different outcomes? 52. Yeah, that would be really sad for each one. So you would need a piece of paper about as big as this room. Okay, yeah. All right, so just clean up a little bit some things that I've circled just to make it a little clearer. Oops. All right. So every new event gets a new set of branching, right? And it branches off of what you've done before. Pretty straightforward. Done it 1,000,000 times. Pretty happy with that. Okay. Well then, let's talk about how to compute the probability. Right? Then what you're going to do is label each branch with its probability. Okay? Now they haven't done this for us here, but I'm going to do it for us. We're going to do it here on this one just for kicks. So when you're flipping a coin, you can get a heads or a tails. What's the probability of getting a heads? 1/2. So probability there is 1/2. What's the probability of getting a tails? 1/2. So you're just going to label them. Now, we're going to multiply these together later. So do you have to use fractions? No, we could also use what? Decimals. Percentages are not so good because you can't multiply with a percent without converting it first, right? So, okay. So label each branch with its probability. So then here, that's a die. Each one of these is going to be 1 out of what? Oh, be careful. 1 out of 6 for each one of the events, right? Each branch. Okay? So be careful. Okay? And then down here, 1/6 as well on all of them. All right? So having lots of events doesn't change the probability for each single event, does it? So label each branch with its possibility. Then follow the branches for the given probability. So, be careful, because if they want a heads then a 4, there's only one branch in this particular case, that leads from heads to a 4. To get to a heads, I have to go from start to the heads, right? And then from there, I have to go down this branch to get to the 4. Do you agree? So all you're doing is reading a map from then on. Now, will some probabilities have more than one branch that satisfies the situation? Yes. So be careful of those. So follow the given branch or branches to the situation, for the situation given, for the given probability. And then simply multiply those to get the total probability. Can I abbreviate probability capital P, and y'all be okay with that nowadays from now? Okay. All right, good. Okay. So again, these are AND situations, so you just multiply them. Yes?
This one is more than one of the same branch.
Okay.
Like what you said before, to be careful. Like if there's 2 4 sort of things. Or they only ask one specific line.
Then that means you'll be counting 2 probabilities, so you'll have those 2 probabilities. It's either this one or that one, so you're going to end up adding them together, the ones that are, right? So it's this branch or this branch. So that would be an or situation, so you'd add them. And we'll look at some of those as we go. Good question. Thank you. All right? Now, if all the branches here are the same, though, and each one of them is equally possible, then you just count them out of the total number. Do you see that here they've listed the sample space at the end? Heads are 1, heads 2, heads 3, heads 4. Right? They've listed all the sample spaces. But if you look at this, there are 6 branch ends there, 6 branches ends there. That means that if you're just counting straight probability right across, it's out of 12, right? But if you have specific probabilities written, then you multiply those. And you end up with the same number. 1/2 times 1/6 is 1/12. So, either way you do it, list the sample space and multiply. Why is it important that you be able to list the sample space and multiply? Because does the AND rule work every time? No. But now here, we're drawing the sample space, so this multiplication rule will always work. Because we're drawing the sample space as well. Okay? You don't have to do this business. I'm not going to expect to see that. It does speed it up a little. So if I say, how many times could you get a heads and a 5? Boom, there it is right there. You don't have to follow the branches to get it. But you don't have to write that out. But you can. Now, we do have to be careful because many times the probabilities aren't even. We'll talk a little bit about that. And also, you can have probability trees where not all the branches branch again. A classic example of that is, let's say that you're going to an athletics competition. How convenient, right? And you're going to run there's a series of 3 races, 3 short races. Well, if you lose 2 of the races, you're out. You're not going to be able to run the 3rd one at all. Okay? So, in that situation, could there be a lose branch? No. You could lose, and then that's where that set of branching would stop. Because you can't if you've lost twice, you can't even run in the 3rd race, right? But what if you had lost and won? Could you then go to the third one? Right? So you see that probability trees are not always perfectly equal and aligned. You're going to have some times when the probability of when the one set of branches will stop. Okay? They simply don't exist. They're not possible. Okay? How's it look? Drawn them 1,000 times. Perfectly happy with this. Okay. Bored to tears. All right. Everybody got everything I've written? I'm going to push the button and it's going to erase it all. You all right? Okay. Good. Okay. So each outcome has a 1 in 12 chance of occurring, right? Because there's one thing out of 12 possible outcomes. All right, a little more detail about these, and these things are very important, and we're going to use their definitions, but we'll also talk about it a little bit if you need to, okay? Probabilities can be used where outcomes are not equally likely, right? For example, okay, let's say that the probability of something happening is 0.6. Well, that means the probability of the other thing is going to be 0.4, the rest of it. So probabilities are not equally likely. Now, the one we just did, probability of heads and probability of tails, they're exactly the same, aren't they? So they're equally likely outcomes. But probability trees are really good for events where the outcomes are not equally likely. Okay? So when this is the case, we always label these probabilities on their corresponding branches. We didn't need to label the branches of the heads and tails and the throwing the die because they're equally likely to happen no matter what happens, right? But if the events are not, then you must put the probabilities on their branches. Okay? So you must label the branches if the outcomes are not equally likely. Okay? Now, here's another thing. The probabilities of an event must add to equal 1. Right? Because this or this is going to happen. It's certain that you're going to get one of the 2 or 3 or 7 or 12 possibilities, right? And what is the probability for an event that is certain? 1. Okay? So, when you're looking at the branches, and I'll pull it down in just a minute and show you what that looks like. When you're looking at the branches, the things that you have on corresponding branches has to equal to 1. Okay? So that's branches coming from the same event must add to 1. Okay? Right. And here we talked about this one. You can multiply these probabilities along the branches to get the probability of the final outcome. So, first one times the second one, just follow the branches first, then put the numbers in, and to get the final probability, we simply multiply them. And the final outcomes, if you did every branch. Now, I do not expect you to multiply out every branch, just the ones you need. But if you did multiply out every single branch, the final outcome might add to 1. Okay? Now, here's a little caveat. I told you I don't expect you to multiply out any of the branches that you don't need. But remember that displaying and demonstrating statistical knowledge above and beyond is what gets you excellence, right? So if you want excellence on a problem or to really impress the graders, then you might go ahead and do all branches and then demonstrate that all of them would add to 1. That shows significant statistical knowledge, right? Now, do you have to? No. Could you probably get excellence just by answering the question very accurately and describing what's happening? Yes. But if you want to kick it up just that one more notch, it's not going to take you very long to run through those numbers with your calculator and add them up to make a 1 to really impress whoever's grading it. Okay? All right. I'm still learning that system too, so we'll look at some before you have to take your exam, which is a practice external anyway. We'll go over one of them together in class from start to finish. We should have plenty of time to do that before you take your practice. All right, so do you see here's a demonstration of what's happening here. Okay? Do you see that these two events, these two are the branches, they're corresponding branches, and 0.7 plus 0.3 equals 1, doesn't it? Oops, I didn't put that in the right spot, but okay. All right. Then, if you're following this branch and this branch, that's 0.7 times 0.6, which gives you 0.42. So that's the probability of both of these branches happening. Right? It's an and statement. Then they did it for every branch, and then they took each one of them and added them together. And what was the result? 1. Because the ends of those branches, all of those probabilities, all have to be a certain event. If it doesn't add up to 1, then you've done something wrong in your math. Okay? So we're just going to read. So, what if I wanted the probability of B and A? Or then A. All right? Well, that means I want B first, and then A second. So B first would be down there, then A second would be right there, right? So that would be 0.3 times 0.8, which gives us a probability of 0.24. And again, you could go through and multiply those out, but you don't really need to. You don't really need to do any multiplication until you know which branch you're measuring. Okay? That's good? All right. Let's see what's next. Right? So probability trees are particularly useful for displaying and calculating probabilities of sequences of events. Right? So in other words, things that happen over time. Like you ran the first race, you ran the second race, you ran the third race. Okay? So sequences of events means that you're looking at things that are happening over time in sequence. Right? But particularly in sequence over time and in order. Okay? So, classic example here. They're talking about what happens with a couple has 3 children. Okay? You're going to find they're going to try to keep things to experiences that you're familiar with. If you have a child, that child can either be a boy or girl and a boy, right? Right? Or boy. So they're going to give you things that are very easy to calculate for you. So let's just draw the tree. Right? We're going to go to a blank page, and we're going to draw the tree for this happening if they have 3 children. So this should be in your examples, right? So here we go. So they don't start with any children, yeah? So we just have plain old start. For the first child, we can either have a boy or a girl. You've drawn these before. You know, keep the branch angles as narrow as you can, because these things can take up a whole page of paper very quickly because they grow exponentially, right? So those are the probabilities for the first child. So the probabilities for the second child are going to be boy and girl breaking off from each branch. So here we get boy, girl. Here we get boy, girl. Yeah? And then finally, these guys are going to have 3 children, so we need to branch again for our third child. So from there, we can branch to boy, girl. From there, we can branch boy, girl. Same thing here. And same thing here. My G's are really bad, aren't they? Right? Doesn't even look like a G. Happy with that? Okay. So now you have it drawn. Mine's going to have to go away because I want to go back to the questions, and then we'll answer the questions. Okay? Let's see. I might be able to. Nope. Okay. Thought I could, but I can't. So now what we're going to do, now think about it. Am I dealing with a case of equally likely outcomes? Are you just as likely to have a boy as a girl? Yes. So these are equally likely outcomes, so I can just use the tree at the end. Okay? How many branches were there at the very, very, very far end? 8. That means that I have 8 possible outcomes that can happen, right? So I just need to count out which ones. Okay? So that total number of branches at the end, as long as they're equally likely outcomes, will tell you what you can have. So they have 3 children. What's the likelihood of all 3 being girls? Yeah, there's only 1 branch out of the 8 that gives you all 3 girls. So the probability of all girls is 1 branch out of the 8 branches. All right? What's the likelihood of at least 1 boy? So is that just 1 branch? No, there are several branches. How many branches are there? Now again, that could be all 3 boys, that could be 2 boys, or that can be 1 boy, right? So at least 1 boy means 1 or more, right? So the probability of at least 1 boy. How many? You bet, because unless you have all girls, then you're going to have 1 boy in the mix somewhere, right? So these 2 are complementary. Have we talked about complementary? Right? So if it's not all girls, then we could just subtract from 1 to get the other ones, right? If 1 out of 8 is all girls, then the rest of them have at least 1 boy in it, right? So you don't always have to go back and count the branches, do you? What's the likelihood of exactly 2 girls? 3 out of 8? Do y'all agree? I don't have it in front of me, so I have no idea. You okay with it? Perfect. Just count them out. And because these are equally likely outcomes, there's no point in multiply thing. You could. It'd be 1/2, 1 times 1/2, right? So, and then add all the branches that you get together would give you the total. All right. So here we go. And here are their calculations and their probabilities. They did them as decimals. They went ahead and wrote the probabilities on there and multiplied them out and got a probability number, right? But if you did the division with those fractions we just got, you'd get the same thing. Now, right? Because if you did 1/8 divided out, it would become 0.125, right? Okay. Now, there they just subtracted from 1 to get the rest of it. And here, this is, Georgia, your question. If you have many branches that satisfy the situation, that means it's this branch or what? This branch or this branch, and or means that you would add them together. And that's how they got the last ones. Okay? But again, if you took 3 out of 8, just like we did, that's the decimal you'd get. Happy with the decimal or the fraction. It makes no difference to me. Okay? All right. Then it goes on into your homework, so let's move into the second part of this. Okay. Some probabilities are going to change after the first event because of non-replacement. This is a critical thing that you must understand in probability. If you replace something, could you draw the same thing again? Yes. And you also have the same number of things in your box or your choice to choose from, don't you? But if I take one out, can I pick that thing again? Nope. And do I have the same number of items left inside the box? No. So replacement and non-replacement are really important. So some probabilities will change after the first event due to non-replacement. Okay? So we're going to look at an example here. We're just going to run through this pretty quickly here so you can do this. But all right, a traveler has a bag of coins that contains 5 New Zealand coins, $1 coins, 3 Singaporean $1 coins, and 2 Australian $1 coins. If 2 coins are selected at random from the bag, and what's the key there? Not replaced, okay? What's the probability that there's going to be at least 1 New Zealand coin? Okay? So first we're going to create our tree diagram. Not all of these are going to be equal probabilities because he has different numbers of coins, doesn't he? For New Zealand coins, he has 5 out of the, how many total coins? 10? Good. And then Singaporean coins, he has, He has 3 of those out of the 10 coins. And then finally the Australian, he has 2 of those out of 10. Now, notice that 5 and 10 and 2 and 10 would reduce. Don't do it. Just go ahead and leave them unreduced, or you could change them to decimals if you want to. But if you're going to do any work with fractions and they have the same denominator, that's a good thing, right? All right. But doesn't matter. You could also change them to decimals. So we know that how many of each thing we have, the probabilities. But we can't just use these probabilities straightforward. We have to be able to construct a tree and then build them up as compound probabilities, because we're going to draw 2 coins, not 1. If we were only doing 1 coin, we'd be done, right? But we're going to do 2. All right. So there we are. There are our probabilities that we just wrote. But remember, after the first coin has been removed, you no longer have 10 coins, you have 9. And whatever coin you got from there also goes down. But if I draw an Australian coin, does that affect the number of New Zealand or Singaporean coins? No. It only affects the number of Australian coins. So look at the probability tree. Okay. We have our start. I like my labels. This is the first draw. This is the second draw. Again, I'm not going to count off, but it just keeps you focused. The first one is the 5 and 10, 3, 10, and 2, 10 that we just talked about, right? New Zealand, Singaporean, Australian. The second draw, notice that all of them went down from 10 to 9, no matter what, because there are simply not 10 coins left anymore.